These are the notes for AP Calculus on the topic of related rates, Part 2 continued. So this one says we've got a person whose height is 5 feet. So on our diagram here, we'll label this. Something that's not changing. So that's a constant in our problem of 5. Is walking away from the base of the straight line along a straight path at a rate of 3 feet per second. Alright, so we can see we've got the street light right here, walking away from it. So that's telling you how the distance from the person to the street light is changing. So let's say we call that x, from right there, right there. So that's giving us dx dt, the rate of change of that. And since x is getting larger here, because he's walking away from the base of the streetlight, it would be a positive 3. Versus if he was walking towards the streetlight, it would be a negative 3. And then it says the height of the streetlight is 20 feet. So that's another constant in our problem. From there to there, that's 20. And we're asked to find what is the rate at which the person's shadow is lengthening. Okay? So the shadow they've drawn for you kind of dark here. You can see that's forms because if you draw a line here from the street light, you can see you'd be blocking the light from hitting the ground right there. So I'll call this S for the shadow from right there to right there. So I know how is that length changing? So we're trying to find the SDT. So we need some equation that relates those two. In this case, notice we've got similar triangles. We've got the large triangle right here and then the smaller triangle right here with these. So for the large triangle, you can see you've got 20 is this side over, to get this side from here to here, that'd be adding these two links up, x plus s. And that equals the corresponding sides on the smaller right triangle here are 5 over s. And then to simplify that, we can cross multiply. So you would get 20s equals, we distribute the 5 times both of these, the 5x plus 5s. So you could take the derivative right here. However, notice we've got s terms on both sides, so it might be easier if we subtract the 5s from both sides. So that would give us our equation as 15s equals 5s. And then you can take the derivative of this equation to get our rates in there. Or if you want to, you could even divide by 5 on both sides first to make it simpler, but either way. So the derivative of 15s is 15 times s and t don't match up, so with implicit differentiation, ds dt equals the derivative of 5x is 5 times dx dt. Again, the variables don't match up. And then we know, after you take the derivative, you can substitute in what we know. We know dx dt is 3. So we have 15 times ds dt equals 5 times 3. Which is 15 also, so to solve for dSdt, you divide both sides by 15. And that would give us dSdt. Equals, well, 15 divided by 15, that's just 1. And then to get the correct units, the units for S, the shadow length in this case, is just a length. So that's in terms of feet in this problem. And the units for time, this problem is seconds. So it is positive because, as you can see, as he walks away, the shadow length is going to get longer here. So it's increasing in size. All right, let's take a look at the next example here. So this one says a cylindrical can of radius 8 centimeters. So let's go ahead and draw that here. There's our cylindrical can. The radius is 8. It's placed in the field. The rate at which the height of the water is changing due to both rainfall and evaporation is given by h of t. Okay. So, and notice the units are centimeters per week. That's another clue. It's a rate or derivative. So we've got some amount of water in this can here. Now here they call this h, which is centimeters per week. But it's a derivative, right? And in order to call this height h, like we normally would, I'm actually going to use capital H here to distinguish it from the lowercase h right here. Because if I call it lowercase h, then that's not correct. Because lowercase, this height here should just be in centimeters, not centimeters per week. So this lowercase h of t actually represents the derivative of this capital H height. So h of t is actually the same as dH dt in this case. That's what they're really giving you, the rate of change of the height. Normally I would call this lowercase, but they already established lowercase h was the rate. And t is measured in weeks, it says. Oh, I didn't write in the radius is 8. And then we're asked to find at what rate is the volume of the water can changing at time 5. So we're trying to find dV dt, specifically at t equals 5. And indicate units of measuring it. All right, so with a cylindrical container, in this case a cylindrical can, well, first we would need an equation that relates the volume to the height. And for a cylinder, that's V equals pi r squared. Normally I use lowercase h, but here capital H, since we call that capital H. And notice we have dH dt right here, the sine of pi over 6t minus 1. And we're looking for dV dt, but there's this r here. So we don't want to take the derivative yet because we don't know dr dt, we're not looking for it. So we can make it simpler with a cylindrical can like this. No matter what the height is, the radius is going to stay 8, a constant. So we can actually substitute that in first. So the volume equals pi 8 squared times h, which simplifies to just be 64 pi times h. And now we can find the derivative, because now we only have d and h. We know dH dt, and we're looking for dV dt. So we take the derivative right there. So the derivative of v is dV dt. The derivative of 64 pi h is 64 pi times dH dt. And then we know dH dt right here is the sine of pi over t minus 1. So we got 64 pi. And this is all times this in parentheses. So sine 6t minus 1. So if we didn't know what time, that's as far as we could go. But notice we're given is specifically at time 5, so let's substitute 5 into that. So we get 64 pi times, when you substitute in 5, it becomes the sine of 5 pi over 6. It's still minus 1. So let's go ahead and figure out what the sine of 5 pi over 6 is. So 5 pi over 6 is not quite to pi. And so there's 5 pi over 6. And it's got the interior angle here of pi over 6, which is the same as 30 degrees. So the side opposite 30 degrees is 1, and hypotenuse is 2. So the sine would be 1 over root 2. So we've got dv dt equals 64 pi and then times the sine of 1 over root 2 and then minus 1. Oops, I apologize. I just realized I made a mistake. I accidentally drew a 45 90 triangle here. Not 1 over root 2. It's 1 over 2. So just 1/2 is the sine of 5 pi over 6, and then minus 1 so we have dv dt is 64 pi, and then 1/2 minus 1, that's 1/2 minus 2/2, or just 1/2 minus 1 is negative 1/2. And you can see 2 goes into 64 32 times, and we still have a negative there. So dv dt is negative 32 pi. And then you get the units. You look at the units of volume, which in this case, the volume is 3-dimensional, so it would be centimeters cubed, since the radius is in centimeters. And the units for time would be weeks. Centimeters cubed per week. And we get a negative answer, which in this case, we didn't know ahead of time, but it means the amount of water in the cylindrical can is decreasing at 5 weeks. All right, so we'll go one more. This one says, at a certain height, a tree trunk has a circular cross-section. So cross-section, remember, is whenever you have 3-dimensional shape, in this case a tree trunk, which we can model kind of like a cylinder, even though tree trunks are not perfect, usually perfect cylinders there. And the cross-section is a circle. So if we slice through a 3-dimensional shape, the cross-section is the 2-dimensional shape we get. So there's our circular cross-section. All right, now it says the radius of that cross-section, here they call it capital R, grows at a rate modeled by this function. And here they actually use the notation we usually use for derivative, dr dt, unlike the last problem. Again, it's not a constant rate, because it's got t in there, and it's millimeters per year. So that's dr dt we know. and t is measured in years. Find the rate at which the cross-sectional area is changing at time 16 years when the radius is 80 millimeters. So we're trying to find the rate of change of the cross-sectional area, just the area of the circle, specifically at t equals 16. So here, even though overall it's like a cylinder, we're really just focusing on what's happening with the circular cross-section here. So what relates the area to the radius is the area, formula for a circle. A equals pi. Normally I'd use lowercase r, but here in the problem they use capital R to represent the radius in both this notation and its derivative. So it'd be capital R squared. And then since we have d r dt, we're looking for d a dt, we take the derivative of that with respect to time, which would give you d a dt equals 2 pi capital R times d r dt. And then we could substitute in, oh, I forgot one more thing. This is when time 16 and the radius is 80. So also when r equals 80 millimeters. So we can substitute in 80 for r and the r dt as well. So the dt will equal 2 pi times, r is, the radius is 80. And then dr dt, we know is 5 times the 432. And then we just have to substitute in our specific time was 16. So d dt would equal 80 times 2 pi, that's 160 pi. And then we substitute in the 4th root of 16. So 16 for time, but the 4th root of 16 is 2 times 5 is 10, and 10 times 160 is 1,600. So our final answer for the ADT, the rate of change of the area of the cross-section, which is a circle, is 1,600 pi. And then the units for area, since the radius is in millimeters, the area is two-dimensional, so it'd be millimeters squared. Over the units for time here are years. And that concludes the notes for AP Calculus on the topic of related rates part 2 continues.